All right, it's 5 o'clock, so we're going to get started. Hello, everyone, and thank you for tuning in to the Flagstaff Festival of Science virtual presentation series. I hope that everyone has been enjoying and attending some of our other events, and I hope that you will continue to participate as we have lots of great presentations still to come. And please remember to give us your feedback by taking the survey that's located on our website homepage, scifest2020.org. And we really would like you to fill out the survey after each event that you attend, so that we can have individual feedback about each individual event. And it just takes 3 or 4 minutes to fill it out. So please fill it out as many times as you can for as many events as you can. We really appreciate the feedback. Also note that on our website, scifest2020.org, you can ask questions to our presenters from this main page as well. So right now, it's my pleasure to introduce our next presenters, Dr. Ken Herkenhoff and Dr. Ryan Anderson of the USGS Astrogeology Science Center right here in Flagstaff, Arizona. Ken and Ryan are both leading experts in planetary science, especially when it comes to the science of Mars. Ken has been interested in astrophotography since he was a child and is happy and fortunate to have been able to make a career out of one of his childhood interests. For more than 30 years and still going strong, Ken has been collecting, analyzing, and interpreting pictures of Mars from orbit and from rovers on Mars's surface. In fact, he specializes in the design and calibration and operation of cameras on Mars spacecraft and Mars rovers. Ryan has been studying planetary science, especially Mars, for more than 12 years. He's an expert in data processing, writing computer code, infrared spectroscopy, and geomorphology, or the study of landforms. I think he's having the most fun when he's zapping rocks on Mars with lasers to try to figure out what they're made of. Both Ken and Ryan are science team members of the Curiosity rover that's been collecting data in Gale Crater on Mars for many years now, and the Perseverance rover that's on its way to Mars right now. And that's what they're going to be talking about tonight. So take it away, Ken and Ryan.
All right, thanks, Greg. I'm going to start here. Let me share my screen first of all. I'll begin by describing the older rover missions, and then hand it over to Ryan to discuss the more recent rover missions, the ongoing rover missions on Mars. So this picture shows sort of a family portrait of test rovers in the Mars yard at the Jet Propulsion Laboratory in California, Pasadena, California, where all of these rovers were designed, built, and operated. You can see down at the bottom the Mars Pathfinder Sojourner rover. At right is the Spirit and Opportunity rover, Mars Exploration rovers, and then on the left the currently active Mars Science Laboratory, nicknamed Curiosity. And there's a couple of geeks there for scale. I've been very fortunate to be able to be involved in all of these rover missions, and want to thank all of you for your support of NASA. So moving on, there's just a few things I want to remind you about Mars. Mars is much smaller than Earth. Its diameter is about 53% of Earth's diameter, but its day just so happens to be about the same length as an Earth day, just 37 minutes longer. And we'll refer to a Mars day in this presentation as a sol. But because Mars is farther away from the sun, its year is much longer than Earth. So its year is 687 Earth days long. Its mass and gravity are smaller than Earth's, and its atmosphere is very thin, mostly carbon dioxide, with a pressure only about 1% of Earth's sea level air pressure. And because the atmosphere is so thin, the temperature at Mars' surface varies widely from minus 220 to about room temperature, with an average of minus 76 Fahrenheit. So because it's much smaller, if you weigh 100 pounds on Earth, you weigh only 38 pounds on Mars. But still, it's arguably the most Earth-like planet in our solar system. And because it doesn't have oceans like Earth does, there's actually more surface area on Mars than there is on Earth. So there's a lot of Mars to explore, and we'll be describing just the earliest days, the first steps in Mars surface geologic field exploration. So the first Mars rover, called Sojourner, was a technology demonstration which landed on Mars in 1997 with the Pathfinder lander. It was parked on one of the lander's pedals and drove off the ramp you can see at the bottom. And at upper right, it's up against a big rock that we named Yogi. The Sojourner rover was designed to last only 7 days on Mars, but it ended up outlasting the Pathfinder lander, which lost communication with Earth after 83 days. So based on that great success of this technology demonstration, JPL proposed more capable rovers that were eventually selected by NASA for flight. In fact, after the failure of the 1999 Mars Climate Orbiter and Mars Polar Lander, NASA asked JPL to send 2 rovers instead of 1 to reduce the risk of total failure. So these are the Mars exploration rovers, dubbed Spirit and Opportunity. They used the same airbag landing system as Pathfinder, which bounced along the surface and then rolled to a stop and opened up like a flower petal. And they were each designed to last about 90 sols on Mars. They were expected to die at about that time because of dust falling on the solar panels based on Sojourner experience. And their primary science goal was to look for evidence of past water on Mars. And so you can see in this diagram a number of instruments up on the top of the remote sensing mast, the PanCam mast assembly. There's a pair of PanCam multispectral cameras, also a pair of navigation cameras, which were wide angle black and white cameras. And the mast assembly also served as a periscope for the thermal emission spectrometer, which was located inside the body of the rover and is sensitive to mineral signatures that could be detected remotely. Then down on the robotic arm, the instrument deployment device, at the lower left, there were 4 more instruments: the alpha particle X-ray spectrometer, which measures elemental chemistry, a Mossbauer spectrometer, which measures iron mineralogy, a microscopic imager, which I'll be saying more about later, and the rock abrasion tool, which abrades fresh surfaces for the other instruments to interrogate. So the microscopic imager is a close-up fixed focus camera designed to be sort of like a hand lens, a geologist's hand lens or a jeweler's loupe, to give us that kind of a view, close-up view of rocks and soils on Mars. The science investigation was led by the USGS here in Flagstaff. And you can see from these details that it's a very old type of camera, just a 1 megapixel array. But this was designed back 20 years ago when those kind of cameras were new for Mars exploration. And you can see that it has a very limited depth of field. So because it's fixed focus, we use the arm to better focus the camera, to ensure that the surface was in good focus. And you can see other instruments, the APXS and the RAT on the turret image taken by PanCam on the left. So both MER rovers arrived in January of 2004. This is a color-coded topographic of Mars, except for the polar regions, showing the MER and other landing sites. So VL1 and 2 are the Viking landers, MPF is Mars Pathfinder, and then you see Meridiani and Gusev near the equator, on essentially opposite sides of the planet. One of the reasons we chose landing sites on opposite sides of the planet was that we could then use a single facility, operations facility at JPL, to run both rovers simultaneously. So the Spirit team would operate that rover at Gusev for 12 hours, and then the other team would operate Opportunity in Meridiani Planum for the other 12 hours. I remember trying early in the mission to follow both rovers and quickly realized that was impossible, and and gave up. So Spirit was sent to Gusev crater, shown here, about 103 miles across, because, as you can see in this color-coded topographic map, it appears that there's a big river flowing in from the south, filling that once filled this crater, forming a lake. So we were expecting to find lake beds on the floor of the crater based on orbital images like this. However, when we got there, we quickly realized that the floor of the crater was buried by lava, not lake beds. So after driving the landing site is the upper left, and we drove first to Bonneville crater, hoping that it had been large enough to poke through the lavas into the lake beds below. No luck, so we literally headed for the Columbia Hills, which by then had been named after the space shuttle astronauts that perished earlier that year, or about a year before that. In part because we expected those rocks in the Columbia Hills to be older than the lavas that partly buried them. And in fact, they were. You can see that the mission lasted much longer than the 90 days it was designed. Both missions did. And that's mainly because the Martian winds occasionally blew dust off the solar panels. We didn't expect that, but that's basically why these rovers lasted much longer than expected. We also survived Martian winters by tilting the solar arrays toward the sun. Now you can see at the lower right a feature called home plate. That's where Spirit spent most of its mission, partly because on Sol 787, the right front wheel drive motor failed. And what that meant is basically the rover had to drag that wheel behind it for the rest of the mission. Fortunately, all of these rovers were designed to drive forward as well as backwards. They have cameras on front and back. So Spirit was a long, great mission, and here's just one highlight of the scientific discoveries made there. This is silica-rich soil near home plate that was exposed by dragging that right front wheel behind the rover, driving backwards, showing this bright material that we wouldn't have known about otherwise. And on Earth, silica-rich soils like this are most often deposited in hot water. So this is evidence of a habitable hot spring environment on Mars sometime in the ancient past. We also discovered carbonate rocks on the south flank of Husband Hill, which was likely also formed by water. So these are the key scientific discoveries of the Spirit mission. About 6 years into the mission, Spirit got stuck in deep sand, and the microscopic imager was used to look at Spirit's underbelly to see if there were any evidence of high centering. And you can see in the center of this picture, it looked like Spirit was in fact high centered on a rock. This is also the only way to view the right and left middle wheels, which you can see here. Looks like they're not completely buried, so that was good news. All of these images were out of focus. We didn't intend to use the microscopic imager this way, but by processing the images, we were able to make these features visible. And this was obviously useful in planning the extrication efforts that unfortunately ultimately failed because we ran out of solar power in the winter. Because we were stuck here, couldn't tilt the solar panels toward the sun as we had in previous Mars winters. So that was the end of Spirit. But after 6 years of what was intended to be a 90-day mission, we really couldn't complain. Opportunity had much better luck than Spirit from the start. This is an image taken from orbit of the Opportunity landing site. The first bounce of the airbags and the retro rockets effect on the surface is shown in the circle just left of center. And the lander bounced and rolled into Eagle Crater at upper left in what the PI, Steve Squires, called an interplanetary hole-in-one. You can also see here from orbit the back shell and parachute and where the heat shield impacted nearby. This is high-resolution image taken much later in 2017, showing the lander and airbags in Eagle Crater, which is about 22 meters across. This was, again, the hole-in-one. And the other lucky part of this is that there were exposures of ancient rocks right around the rim of the crater, so we didn't have to drive far to interrogate those rocks. And here's what we found. Among the things we found, the spheral morphology in MI images showed that many of these spherals that we found and were dubbed blueberries were double or triple connected concretions, showing that they formed in place by underground precipitation in this case, acidic water. These are iron-rich and also found on Earth. Hematite spherals are also found in acidic environments. So Opportunity found evidence of ancient Mars water very early in the mission. And then there's a long mission, and so just very briefly, the traverse from Eagle Crater to Endurance Crater and Victoria Crater took years. But once we had gotten that far, we realized that there was nothing really limiting the life of the rover. And so we were looking ahead to where to go later in the mission. And by this time, the Mars Reconnaissance Orbiter had returned data, remote sensing data from orbit, showing evidence for clays in the rim of this big Endeavour crater, about 22 kilometers in diameter. Clays are common on Earth because water is common on Earth. And seeing clays on Mars indicates that there was neutral water, less acidic water on Mars in the distant past as well. So even though it was very far away, we decided that's a great target for the mission. And you can see the traverse in yellow here from Victoria to Endeavour Crater, where Opportunity arrived in August of 2011, 3 years after leaving Victoria Crater. And here's what the Endeavour Crater rim looked like when we got there. The older rocks are the high ones in the background, and they're partly buried by the sulfur-rich sediments that we had been exploring previously during the mission. In this view, the color is enhanced, so the sky is actually reddish, not blue as shown here. And sure enough, those older rocks showed evidence for more clement environment, more Earth-like environment. In particular, here we found gypsum, a vein of gypsum, shown in PanCam at upper left and then blown up in an MI mosaic at the right, lower right. This evidently, gypsum probably precipitated from low temperature, less acidic waters than those that formed the sulfur-rich sediments that we'd been exploring previously in the mission. So again, this is evidence of an Earth-like environment and possibly habitable in the distant past. The Opportunity rover completed the first Mars marathon in 2015. It also broke the previous record for any extraterrestrial vehicle that was set in 1973 by the Soviet Lunokhod 2 rover at 39 kilometers. So that was cause for much rejoicing. And the great thing about that is allowed us to continue doing geologic investigations, field studies of the rim of this crater. In particular, we got far enough south along the rim to this feature called Perseverance Valley that looked from orbit like it was eroded by flowing water. It had kind of a sinuous, braided appearance that was very attractive for exploration. And so we eventually got there and drove down into it. And on Sol 5000, finally took the only Opportunity or Spirit selfie using the microscopic imager. You can see that the images are out of focus. Again, the MI was not designed to take these kind of pictures, but I'm glad we did because this was very near the end of the mission as we were exploring Perseverance Valley. It turns out that Perseverance Valley was probably not eroded by water. We can't rule that out, but it looks more likely that it was formed by faulting along the rim of the crater. Then in 2018, there was a global dust storm on Mars, and this shows a simulation of what the sky or what the sun would have looked like in the sky from Opportunity as the storm approached. At the far left, opacity of 1 is pretty normal. That's kind of a hazy day on Earth or Mars. And you can see as time went by, the opacity increased. The sun was eventually blotted out. The highest opacity measured on Mars was from the surface was observed during this dust storm. On Sol 5111, the opacity was over 10.5. And because there was almost no sunlight falling on the solar panels, Opportunity suffered a low power fault, meaning it didn't generate enough energy from its solar panels to keep it alive. And that was the last we heard from it on Sol 5111. And the mission was declared complete February last year. But again, we can't really complain. 5,111 sols for a 90-day mission is pretty good. So again, based on these successes, JPL proposed an even more capable rover. There were a bunch of larger instruments that NASA wanted to fly to Mars, but were too big to fit on the MER airbag entry, descent, and landing system. That was about, the MER rovers are about as big as you could land on Mars with that system. So MSL used a completely new landing system. Instead of airbags, it used rockets and for the first time, guided entry. And instead of solar panels, it needed more power than you could generate easily with solar panels. So it's nuclear powered as a radioisotope thermoelectric generator on its back. And it landed in August of 2012 successfully, and is now in its 3rd extended mission. Both Ryan and I are currently working on that mission, and I'm going to turn it over to Ryan at this point to let him tell you about these currently operating missions.
All right, thanks, Ken. Yeah, so the Mars exploration rovers, they set the bar pretty high for a rover mission on Mars, but Curiosity was the next step. And so if we go to the next slide. So the Mars exploration rovers, their main goal was to look for evidence of water and understand the history of water on Mars. Curiosity, the goal was to sort of take that to the next level and look for evidence of habitability. That is, we know there was water, but was it safe for life? So these 4 bullets sort of summarize what the Curiosity rover is looking for biological potential that is safe for life, the building blocks that life needs, understand the geology and geochemistry, so we can understand what happened in the past and how the Mars surface has changed over time. Of course, the role of water is very important in all of that. And then also it carries some instruments to understand the amount of radiation that is hitting the surface now to figure out how habitable it is for a future astronaut. So if we go to the next slide. This is a computer-generated picture of the rover, but it's very realistic, and it shows, it has all the different instruments labeled. And it's a very international team. As you can see, we've put the flags of the partner countries involved in some of these instruments on here. But very briefly, the reason we call this mission the Mars Science Laboratory is that it carries so many very capable laboratory instruments. So it has a large robotic arm with a drill, a scoop, brush, sieve, so it can take samples. And that arm also has a color camera, MOLLE, as well as an APXS, just like the previous rovers, to do chemistry of the rocks up close. The samples collected by the arm are fed to the laboratory instruments inside the rover, ChemIn and SAM, and those can look at the mineralogy and chemistry of the samples. The rover also has some environmental instruments. So DAN shoots neutrons down underneath the rover and sees how many bounce back, and that measures how much water is in the ground under the rover. It has REMS, which is a weather station, RAD, which measures radiation. It also has some remote sensing instruments Mastcam does color, high resolution color pictures of the surroundings. And ChemCam is the instrument that Ken and I both are involved in. ChemCam is a telescope that can take pictures, but it also shoots out a laser, zaps a little bit of the rock near the rover, and then collects the light from that spark that's created, and it can use that to tell what the rock is made of. So if we go to the next slide. So we have this really, really capable rover. We had to figure out where to send it. And so the landing site that was chosen is Gale Crater. And you can see here on the left, the landing site itself is the oval. You don't want to land on top of a mountain with these rovers. It's pretty tricky to land on rough terrain. So we look for a flat spot. But in Gale Crater, we get a flat spot right next to a big mountain of layered rocks, which is a great target for geology. So you can see on the right, there's a fan of sediment coming down off the crater rim that we land near. And then as we climb up onto the mountain of layered rocks, geologists love layers because layers signify a change in the conditions. And so as we work our way up that mountain, we can understand the changing conditions on Mars. So next slide. And as Ken alluded to, this rover was too big to come down in the traditional way of bouncing in airbags. So the engineers at NASA came up with an even crazier way to land, which is to dangle from this flying jetpack platform. This is called the Sky Crane. It looks crazy, but it is the best way to land something this large on the surface, and it worked perfectly. So next slide. So here is a high resolution orbital view of the landing site sometime after we landed. So on the left, you can see this area labeled Bradbury Landing. It's sort of smudged. That's where those rockets from the Sky Crane blew away the dust. And then you can see some faint rover tracks continuing to the east from that location. And then sort of in the middle right of the image, you can see sort of a bright spot. That is the actual Curiosity rover as seen by that satellite when this picture was taken. You may be wondering, why are we driving to the east when our target was that mountain that was to the south of where we landed? And the reason is, you can see labeled in white, there were 3 geologic units that were all in contact at this location called Yellowknife Bay. And we decided it was worth a little detour to go take a look and understand what was going on with those units and go make our first measurements with the robotic arm in Yellowknife Bay. So next slide. And it turned out to be a really good idea because Yellowknife Bay, once we started taking a closer look at it, it turns out those fractured rocks that we could see from orbit, when we got up to them and studied them up close, they are mudstones from an ancient lake bed. And we drilled into them, fed our first samples into the laboratory instruments, and we found that there was evidence for water there. And not only that, but that the water was safe for life. It was not too acidic, it was not too salty, and the minerals present had a lot of the chemicals needed for life to exist. And in one of the drill locations, we even were able to detect the first complex carbon-bearing molecules on Mars. So all in all, it was a pretty successful first drill location on Mars, but it's just the tip of the iceberg of what Curiosity has accomplished. So if we go to the next slide. So this is a map of the rover's traverse so far. So you can see at the very top, Bradbury Landing is labeled in blue. Our detour to Yellowknife Bay is just a little bit to the right. And then since then, we've been driving southwest to get around this long line of black sand dunes because we can't cross those sand dunes. And then we crossed from the crater floor onto the foothills of Mount Sharp. And we are currently working our way up the layers of Mount Sharp into the clay-bearing unit that was so interesting from orbit. So if we go to the next slide. So all that driving takes a toll on the wheels. And at first we were still learning the capabilities of the rover, and we put some holes in our wheels. Turned out the rocky surface that we were on could punch right through the aluminum wheels of the rover. And so we learned our lesson, and we started driving more on sand and avoiding those really rough, rocky areas. And so even though it looks bad, the wheels are still working fine. We're keeping an eye on them, but now that we're being careful, the wheels should last us a good long time and let us continue the mission. So if we go to the next slide. So along that drive, we encountered some really interesting layers. There are these tilted layers that you can see in the top image. It's a little bit hard to see that they're tilted, but when you get up close to them with the rover and look at them from different angles, they're tilted. And in this picture on the lower right, you can see tilted layers tend to correspond to a delta, where you have water flowing down and being deposited into standing water, and it forms these sort of slanting layers. And then as we continued and got onto the foothills of Mount Sharp, we switched over from tilted layers to these flat lying layers. So we think what we were seeing was a transition from delta deposits to lake bed deposits at the base of Mount Sharp. So again, more evidence for habitability, and definitely very interesting geology that we're seeing along the traverse. Yeah, go ahead, next slide. And then, as I said, we were trying to get around these sand dunes, but the sand dunes are also very interesting. So we did stop at an active sand dune. In the images from orbit, taken years apart, we can actually see these sand dunes moving a little bit. So we wanted to take an up-close look, understand what was going on in these sand dunes, make a lot of measurements there. You can see we've actually driven into the sand and made a big scuff with our front wheels, so we can see what's happening underneath the surface of the sand. One of the interesting discoveries that came from looking at these sand dunes is that they have the small ripples that you're used to seeing on sand dunes on Mars and on Earth, and sand dunes are pretty common on Earth, but these medium-sized ripples are unique to Mars. It's a combination of the low atmospheric pressure and low gravity that cause this sort of third middle-sized type of ripples to form on the sand dunes on Mars. So next slide. So this is back to a reminder of where we are. So we went past those dark sand dunes. Now we have crossed over this sort of light colored ridge toward the bottom of the picture called Vera Rubin Ridge. And we're now up in this trough that contains clay minerals that we have seen from orbit. If we go to the next slide, this is where we are as of a few days ago. We're just off. Yeah, so right there is where we've been sitting for quite some time, actually. We drove back downhill a little bit to get at a certain type of rock, and we've been doing a lot of drilling and analysis in this location for the last couple of months. So if we go to the next slide. And so here's a sort of a photo gallery of most of the drill holes that we have drilled on Mars. We've come a long way since Yellowknife Bay. And you can see the color of these drill holes varies. Some of it is lighting, but a lot of it is the actual rocks are different colors once you drill into them. There are 2 drill holes missing, and those are the 2 from our current location at Mary Anning. And so we're still working on those, and there's a 3rd drill hole at our current location being planned before we move on. So next slide. So this animation shows the sort of future of the mission. We're currently at the point of the white line, sort of where it comes into contact with what's called the green hue pediment on this image. And we're going to continue driving uphill through the clay bearing unit, take a little detour to check out something interesting over here on the left, and then drive up into what we're calling the sulfate bearing unit, up onto the green hue pediment, and then investigate this ridge that's labeled in red, the Geddes Vallis Ridge, and up into the channel. So this is going to keep us busy for years to come. There's tons of fascinating geology yet to come with this mission. So it's been very successful and will continue to be successful for as long as we have power, which it just depends on the decay rate of our plutonium power source. So next slide. So I thought I would throw in a couple of recent pictures from Mars. So this came down just the other day. This is a view from the nav cams. These are the low resolution cameras, black and white, that we use to get our bearings and look at our surroundings. This image was actually taken in an effort to look for dust devils near Mount Sharp. So you can see the foothills ahead of us and the sort of lighter colored Mount Sharp towering up on the horizon. If we click, I think a box should appear. Yeah, so this box, there's some interesting outcrops here, and we've actually used the telescope on ChemCam as sort of a spyglass to look ahead and look at this outcrop. So if we go to the next slide, this is a stitched view of 3 different observations of this area using the ChemCam telescope. And this is another case of an instrument being used sort of beyond what it was originally planned for. The telescope on ChemCam is mostly there so that we can tell where we hit with the laser for targets that are close by. But we have figured out how to use it for long distance observations as well. And it gives us these beautiful views of the complex geology that's up ahead of us, sort of a sneak preview of what we'll be getting into in the coming months. So next slide. And I figured I'd also show another couple pictures. On the left is the HazCam, sort of a fisheye lens view of what's in front of the rover. You can see the rover's arm peeking out from above and the wheels on either side. And then on the right is a Mastcam view of the inlet to one of the laboratory instruments. And we always take pictures of these inlets when we're doing laboratory analyses to make sure that everything is working fine, that things don't get stuck open. And it's also an interesting picture because if you look at the nice white rover deck, you can see it's just completely covered with blown sand and dust from being on Mars for years and years. Luckily, we're not solar powered though, so it's okay. So that's where the Curiosity rover is. In the last few minutes, I'm going to talk about the Perseverance rover, which launched on July 30th and is currently on its way to Mars and will be landing in February. It has the same basic design as MSL, it's the same size, but it has some new instruments and sort of new overall goals. So if we go to the next slide, here's a picture of the launch. You can see on the left the rocket taking off, and then on the right a beautiful aerial view of the rocket lifting off early morning from Florida. So it was too bad that we couldn't all be there to see the launch in person this year, but the main thing is that the rocket launched safely and is on its way and everything looks good. So we're excited to see it land in a few months. So next slide. So again, like the Curiosity rover, this is a large rover with lots of capable instruments, including instruments contributed by multiple countries. And the primary goal of this mission is to really get at the question, did life ever exist on Mars? And part of the answer to that is to collect samples of the surface that can be eventually returned by a future mission. So that we can take a look at them with all the laboratory instruments that we have here on Earth. So Perseverance has SuperCam, which is like ChemCam, but also does some other types of spectroscopy. It has Mastcam Z, which is like Mastcam, but can zoom. It's not just a fixed focal length. It has Sherlock and Watson. Watson is very similar to the Molly hand lens camera on Curiosity. Sherlock is a spectrometer that is really good at looking for organic molecules. Pixel is sort of a next generation APXS. It can do chemical analyses, but it can sort of make a picture of the chemistry rather than just taking a spot. RIMFAX is a really cool new instrument. It's a subsurface ground penetrating radar, so we can actually see the layers of rock beneath the rover, really help us understand the stratigraphy. And then MOXIE is an experiment to see if we can actually produce oxygen from the Martian atmosphere as a precursor to sending humans someday. So next slide. The heart of this mission, one of the main goals is to collect these samples. And so I won't go through all the details of this, but the sampling and caching system is extremely complex. It has the capability to collect 42 little tubes containing either a rock core or soil scooped up from the surface. It seals them, hermetically sealed, and encapsulates them in these little tubes. So if we go to the next slide, you can see what these look like. They're not big. You can see this person's hand holding them. But these tubes will be collected by the rover and then dumped on the surface in what we're calling a cache for a later mission to pick them up and launch them into space and then eventually be returned to Earth. So that's sort of the future of Mars exploration after the Perseverance mission. So next slide. And so this is where we're going. Just like for Curiosity, we're using a very similar landing system. So again, we want to find a nice flat place to land, but near some very interesting geology. And in this case, the interesting geology is this delta system. So you can see this curving valley coming in from the west. It breaks through the crater rim, and then it ends in this sort of fan-shaped feature that is a delta that's preserved and that we can explore on the surface. So if we go to the next slide. This is a picture of the geologic map. This is an oblique view of the map that the rover team has put together, and you can see the different colors are different geologic units, and all the greens are units that have carbonate minerals in them. Those are minerals that form in neutral water, minerals that we have not really seen much of on Mars before. but they're very interesting here. And then the blue units are the delta units, and the dark blue in particular are very interesting to scientists who are trying to piece together the history of water on Mars. So if we go to the next slide, this is a close-up of what you see in those dark blue areas. And these curved layers are evidence of meandering river channels. So that means the water was flowing for a while, long enough for the river channels to drift back and forth, crisscross each other, cut off the deposits made by previous river channels. So these curved layers truncating each other, they tell a complex story of the history of water in Jezero Crater. We're hoping that if we go there and we study them, we can learn about not only the history of Jezero, but the history of water on Mars and what the conditions were like when that water was flowing. So if we go to the next slide. So I said that this mission has basically the same landing system as Curiosity. There is one key difference though. The Perseverance rover is using this new technique called terrain relative navigation, where the rover can actually take pictures as it is descending, compare those pictures to an orbital map, and then if it sees that it is heading toward an obstacle, like a cliff or a crater or a sand dune where it would not be safe to land, it can actually divert where it's landing and come down somewhere safer. So if we go to the next slide, USGS astrogeology here in Flagstaff has actually played an integral role in this landing technology. We made the maps that the rover will be using to check and make sure that it is landing safely. These are the most precisely aligned image mosaics of Mars ever made. And we made two maps. One was a really high resolution mosaic that's shown here. One was a slightly lower resolution mosaic. So the high resolution mosaic was used to find the hazards. Humans went in and marked up the hazards. And then the lower resolution mosaic is on board the spacecraft right now. And it will, as it's flying down and landing on the surface, it will compare what it's seeing in real time with what's on that mosaic and the location of those hazards and divert if necessary to land in a safe spot. So we can get our landing ellipse right up close to this delta, despite all the cliffs and things at the edge of the delta, and get as close as possible to the really interesting geology right from the get-go. So go to the next slide. So this is another oblique view of that product that we made looking out over the delta. So mark your calendars. The Perseverance rover is landing on February 18th in 2021. It should be a really exciting mission and lots of spectacular geology, as you can see. So stay tuned. There's a lot more interesting stuff to come from Mars. So the next slide, I believe, is our ending slide. So if you want to learn more about the Mars rovers, there's some links here. You can follow the Twitter accounts for the two active rovers. Ken and I and others on the Curiosity mission also do daily blogs of what the Curiosity rover is up to. So you can get the latest information, see a few of the latest pictures. So please do follow along. There's lots of exciting stuff happening. And with that, I think we will open it up for questions.
All right. Thank you, Ken and Ryan, for that. That's amazing. I didn't know all that. That's really cool. What's going on right now is amazing. So I just want to remind everybody to go onto the website, scifest2020.org, and submit any questions you have. You just go to the box there that says submit questions to the live event, and you can submit your question and we'll get it and relay it to Ryan and Ken. So the first question I want to ask is from Vinny in Flagstaff. He wants to know, how do you tell the rover what to do?
Do you want to take that, Ken? Go ahead.
Okay, yeah. So the way we tell the rover what to do is, so it's important to understand that the Mars is too far away for us to control the rovers in real time, like with a joystick. So as fun as that would be, we can't do that. So instead, what we do is the rover sends us the data from the previous day, and we take a look at the pictures as a team. The scientists look at what the rover sent us and what's in our surroundings, see if there's any interesting rocks or interesting features that we haven't seen before. And then the science team will come up with a set of targets, and we say we want to take a picture of that, we want to zap that with ChemCam, maybe we want to reach out the arm, take a closer look at that rock, or maybe we're doing a drill day or a drill plan, which actually takes a few weeks. And so maybe we're looking at the results from, yeah, it looks like that rock is safe to drill, or no, it's not safe to drill. And so based on that information, we put together a plan. We have a set of activities that the rover needs to do. We send that to the engineers. They make sure that all those activities are safe and that they will be successful. And then those activities are transmitted up to the rover as a radio transmission, as a set of instructions for the rover's computer to do. The rover receives that, follows those instructions, and then sends back its new data, and we repeat the process. And we usually do this every other day. Sometimes on a weekend or a holiday, we'll plan multiple days in a row. But for the most part, we wait for the rover to tell us what it saw before we decide what to do next.
All right. So we have another question here, and I don't know if you want to stop sharing your screen so we can you can see both of you if you want to. There's a question here from Dave, and Dave wants to know, have you found any organic compounds on Mars?
Yes, I can take that one. We found organic compounds, as Ryan said, even right away in Yellowknife Bay. And since then, we continue to find a variety of organic compounds. I'm not an organic chemist, so I can't tell you precisely what the names are, but what's interesting is that these organic materials are found only a few centimeters, a couple inches below the Martian surface. There's long been concern that the radiation that continually bombards Mars's surface would destroy any organics that might be there. And in fact, we do know from the RAD instrument that there is quite a bit of radiation falling on Mars. But the good news is that there's still a record of organics preserved just a few inches below the surface.
Okay, cool. There's another question here from Isaiah in Flagstaff. Isaiah asks, what if something bad happens with the rover? And there's a similar question, what do you do? What if something on the rover breaks?
Ryan, do you want to take turns? I don't know.
Sure. Yeah, I don't know how we would want to do this. Yeah, so the problem with sending something to Mars is there's no way to fix it. So if something on the rover breaks, it's probably broken for good. There's a lot of clever things that we can do to work around things that break, or if something starts to break, we can try to make it not break anymore, like the wheels on the Curiosity rover. We started to see damage happening to the wheels, and so we changed how we proceeded so that it wouldn't get any worse. The drill on Curiosity had a problem a while back, and we had to come up with basically a completely new way of using the drill. But it works. So it's broken, but we found a way around it. The engineers at NASA are very good at their jobs, and they tried a million different things, and they found a way to drill with the drill sticking out rather than retracting it and sticking it back out. And so we're still able to drill holes in Mars, still able to get samples. It's not quite as nice as it was early on, but it still works, and we can still do good science. So usually what happens when something breaks is we just find a way to live with it and work around it. I don't know if you want to add anything, Ken.
I guess all I'll add is that, it reminds me, one of the most fun things about working on these missions is the ability, the chance we get to work with really brilliant engineers. These guys at JPL not only figure out how to get these things safely down to the surface of Mars, which is not easy. They have been able to, recover from problems like the drill getting stuck. We haven't really talked about that, but they found a way to work around it, and it's just really exciting to work with all these engineers at JPL.
All right, great. So yeah, we've got another 10 minutes to go, so keep the questions coming in. There's another question from Kathy in Flagstaff, who first she just wants to thank you for your presentation. It's awesome. And you mentioned that the rover is going to land on February 18th. She wants to know if you know the exact time of the landing, because she's going to put it in her planner.
Oh, Ken, do you know the exact time? I don't.
I should have looked that up. I think it's late morning. I'm not sure.
Yeah, I
Sorry.
just figured out, check the time when it comes closer. I just have the day marked off right now. It may be on the NASA website if you just search for the Perseverance rover mission.
Okay.
Yeah, and I'm sure it'll be well advertised.
Yeah.
Yeah, it will be. It will be. We'll probably do something here to celebrate, right? Hopefully.
Yeah.
Hope so.
Yeah. Okay, another question. This one comes from Virginia in Flagstaff. She wants to know if there's so many rovers on Mars now, so many, a few, will they ever meet each other?
No. There, you know, like I said at the beginning, Mars has more land area than Earth. So, you know, it may look like some of these vehicles are close together on the surface in the maps we've been showing, but it's still hundreds, thousands of kilometers or miles apart. So yeah, very unlikely that these rovers will ever meet. There's still a lot of Mars to discover,
Yeah, it's a big place.
to explore. You know.
Another question. This is from Tanya in Flagstaff. What are some challenges faced during previous missions which you hope to avoid with future explorations? I have to think about that one.
Yeah, well, I'll let you think while I give an immediate answer.
Go for it.
So my immediate answer is one key lesson learned from Curiosity is make the wheels stronger. And so for Perseverance, the engineers have found a different design for the wheels that is a little bit heavier, but a lot stronger. And so we don't anticipate having that same problem where a sharp rock can puncture through the metal of the wheel. And so they made that work. And I guess another example, and then I'll let Ken answer, is another thing that broke on Curiosity is the ChemCam focusing laser. It uses a laser to shine on the surface and figure out whether it's in focus and shifts the camera. So that stopped working, and we had to figure out a new way to focus. And so the new way to focus is just to take a series of pictures at different distances, at different focuses, and see which one is sharpest. And so the interesting thing about this is that method actually is better for these long distance images. So it's much better that focusing laser doesn't work out past a certain distance. And so we were sort of focusing in the blind before. So we invented this new way to focus, and now it's better. So that's what we will be using going forward for long distance observations. So Ken, do you have any?
Those are good. Another thing I can think of is telecommunications. We've also already overcome some of those challenges. Early on in Mars exploration, we had to send all of our data directly from the spacecraft back to Earth, and that takes power and is slower than the methods that are now being used, and that's relaying data to orbiters as they go over. Typically, orbiters pass over the rovers twice a day, and we'll send a burst of data to them, up to a gigabit of data to some of these new orbiters, including MAVEN, the NASA MAVEN orbiter, and the European Trace Gas orbiter. They both have better radio receivers and can return much more data than we used to be able to return. It was the amount of data we could return daily was a serious constraint on the MER missions. We had to plan that very carefully. That's much less of a problem with MSL now. So we're hoping that the orbiters that are already there will survive till Perseverance gets there and completes its exploration, because we really need them.
Okay, cool. All right, we got a couple more questions. We want to try to end right at around 6, so we have a few more questions. This is from Brandon in Flagstaff. How often do major dust storms occur, and are they a problem for nuclear-powered rovers?
I could take that one if you
Okay,
want, Ryan. Major dust storms do not occur every year. It's every few Mars years on average. Of course, our record only goes back to the 50s, really, when telescopes and cameras were good enough to really track dust storms on Mars. But based on that record, 70-year record, whatever it is, it's every, couple Mars years. They're typically in the southern summer, and they are not a problem for the new nuclear powered rovers, except they cool the surface down enough that we need to heat up equipment more than usual when there's a dust storm, for example, over MSL, Curiosity. Typically, we need to heat things up anyway. It's so cold on Mars that motors don't work well, electronics have to be kept warm, and that all takes power. And so, yeah, you just need a little more of the nuclear power source than usual during dust storms. Otherwise, it's not a problem.
Okay. Here's another question from Dwayne in Flagstaff. Will Perseverance have any seismic instruments on board?
Yeah, so that's one of the shortcomings of a rover, is that you can't really do seismic experiments on a vehicle that's moving and shifting and unstable like that. So Perseverance will not have any seismic instruments. There is a mission right now called InSight that is a lander that is on Mars and active, and they have a seismic instrument. And the way it works is they take the instrument, they actually place it out on the surface away from the lander with a sort of flexible tether, so that vibrations from the mechanisms inside the lander don't affect the instrument that's on the ground. So Perseverance won't be doing that, but there is a mission that is doing seismic studies, and it's definitely sort of an unexplored aspect of Mars to understand what's going on with the seismic activity in the subsurface. So if you want to learn more about that, look up the InSight mission.
Okay, cool. And I think we have time for one more. Anne in Flagstaff would like to know, I think she wants to become a scientist someday. What kind of education do I need to get a job like yours?
Well, I don't want to discourage you, but it takes a number of years to get a doctoral degree, a PhD, which is what most scientists get before they find a job. It varies from depending on what type of science you want to do, but let's say typically about 4 years of graduate school is required. That's after typically 4 years of undergraduate. So you have to get a bachelor's degree and then go to graduate school for another few years to get a master's or PhD before you can typically compete for scientific positions. But personally, I enjoyed graduate school. It was a good time to sort of follow your nose, explore, scientific research problems that might be interesting. And if it doesn't pan out, well, I'll try something else. So I encourage you to give it a try.
Yeah, I'll just briefly say, maybe we could both say our path. I studied astronomy and physics in undergraduate for 4 years, and then I went to graduate school for 5 years in an astronomy department, where I also learned some geology and got involved in the rovers. But in general, studying math and science, but not neglecting writing and communication, because all we do all day is write emails and communicate and give talks and write papers. So it's all very important, but if you want to do the sort of work we do, the math and science is especially important.
Great. Well, thank you both very much, Ken and Ryan, for a great presentation, as always. Thank you to everyone who tuned in to watch. And please remember to fill out the feedback survey after the presentation. Give us your thoughts on what you thought about it, and see you at the next Festival of Science event, which actually the next one starts in about half an hour. So take care.
All right. Thanks, everyone.
Thanks.
Thanks, Greg. Thanks, Ryan.